In this session we're going to look at the aldehyde and ketone molecules, and we're going to begin by looking at their physical properties. So we see here we've got an aldehyde on the left hand side and we've got a ketone over here on the right. This aldehyde here would be propanal on account of 3 carbons in the carbon chain, and a carbonyl group, that's a double bond between a carbon and an oxygen atom at the end of the molecule. Here, where we have the carbonyl group on a secondary carbon, so a carbon that's connected to 2 other carbons, this one we would call a ketone, and this would of course be propanone. ONE indicating the ketone. The carbonyl basically is on one of the middle carbons, not the end carbon. So the first thing we're going to do is to look at the physical properties, so that's things like boiling point, solubility. And what influences that in the case of the aldehydes and ketones is the presence of this carbonyl group, which is a polar bond. And what that means is the oxygen atom, that is what we call more electronegative, located further to the right of the periodic table than carbon, and therefore it's got a relatively high number of protons in its nucleus, which pulls these bonding electrons. There's a stronger attraction to the nucleus of the oxygen than the carbon. The bonding electrons get pulled a little bit across this way, and it therefore gains a partial negative charge, the delta there indicating a partial negative charge. And so we have this dipole with the carbon partially positively charged and the oxygen partially negatively charged. And what that means is we can have an attraction, what we call a dipole-dipole force, between this molecule and the neighbouring molecule. So for example, if I was to draw out another molecule of propanal, which I could draw here, what we have is the possibility of an interaction between these dipoles, dipole-dipole interaction, which would hold this molecule together. Now that dipole-dipole interaction is a much stronger attraction than we would have between alkane and alkene molecules, for example, that rely simply on van der Waals forces, which is a much weaker type of intermolecular force. So the first physical property we'll see here is that the boiling points of aldehydes and ketones, certainly the short chain ones, will be significantly higher than alkane or alkene molecules of a similar size. So for example, ethanol with 2 carbons in, an aldehyde with 2 carbons in, has a boiling point of 20 degrees Celsius, which will mean that it's a liquid just at room temperature. Whereas, for example, propane, which would be an alkane of a similar size, similar relative molecular mass, propane would be a gas. It would have a much lower boiling point than ethanol. And that's because ethanol has got these dipole-dipole forces between the molecules, which are stronger than the van der Waals forces that an alkane, such as propane, would rely upon. Although this dipole-dipole force is stronger than the van der Waals forces in alkanes and alkenes, it is weaker than the hydrogen bonds that hold alcohol molecules together. So for example, ethanol, 2 carbon chains, is propanal. Ethanol, which would just have 2 carbons in, has got a much lower boiling point than ethanol, for example, which would be significantly higher. So there we are, differences in boiling points. Boiling points are going to be lower than equivalent or similar alcohols, but higher than alkanes and alkenes. A similar story with solubility. So the short chain aldehydes and ketones will tend to be soluble in water. They'll be soluble in water on account of they can form interactions with the water molecules using this dipole. The longer chain aldehydes and ketones, not so much, because as the chain gets longer, the hydrocarbon chain becomes more significant, and the carbonyl group here becomes less significant as the chain gets longer. So what you'll tend to find is the short chain aldehydes and ketones will be soluble in water, but as the chain gets longer, the solubility will decrease. Well, what about the chemical properties of the aldehydes and ketones then? Well, the first reaction we'll look at is oxidation. Now, we've actually seen oxidation of aldehydes and ketones before when we've looked at alcohols, because we know that a primary alcohol is first oxidized to a aldehyde, but then that is also then oxidized if you provide oxygen using an oxidizing agent. That can be oxidized to a carboxylic acid. In the case of propanal, we would oxidize to propanoic acid, which we can see here. And the typical oxidizing agent, potassium dichromate, which turns orange to green when it causes oxidation, and that's acidified, it's in acids, so sulfuric acid, hydrochloric acid, doesn't matter, H plus ions from an acid, and potassium dichromate together will provide the oxygen needed to oxidize this molecule, the aldehyde, into a carboxylic acid. But here, if we try and oxidize a ketone, no reaction will occur. Okay, so whereas a lot of the reactions of aldehydes and ketones are very similar, one that is different is oxidation, because we can see here that an aldehyde, the carbonyl group at the end of the carbon chain, is oxidized to a carboxylic acid, but a ketone will not undergo any reaction. The potassium dichromate stays orange, it doesn't oxidize the ketone at all. One of the key reactions that both aldehydes and ketones undergo is nucleophilic addition. And a good example of nucleophilic addition is when we react with hydrogen cyanide, and that would produce this molecule. And that is an example of a nucleophilic addition reaction. Now, the reason that's nucleophilic addition is basically the hydrogen cyanide here is going to produce some cyanide ions in solution. So we can actually, if you want, look at the reaction mechanism that would actually take place here. And we're relying on the fact, really, that this carbonyl group is a polar bond. And so essentially what's happening is something like this. And we start with our aldehyde in this case, but it could be a ketone. And what will happen, because this bond is polar, the negative cyanide ions are attracted to this partially positive center. So there's a pair of electrons initially on the carbon here, the cyanide, are used to form a covalent bond to this carbon, and at the same time one of these carbon-oxygen bonds breaks, and the pair of electrons in that bond is completely transferred across to the oxygen to give it a negative charge. And so we get an intermediate produced, which will look like this. And what we have then is a second stage, where basically that intermediate that we've produced reacts with a water molecule, and basically that pair of electrons there on the oxygen forms a bond to the hydrogen. That OH bond breaks, transfers its electrons across there to the oxygen, and so what you get formed is basically an alcohol group on the end. Of course, we'll also get a hydroxide ion there. And there we are. That's the reaction overall. And the overall reaction that's occurred is basically this, but that's the stages that's actually occurred. You can see why we call it nucleophilic addition, because basically it's a nucleophile. An electron-rich species that's attacking an electron pore center is called a nucleophile, and we're basically adding that into the molecule. It's an addition reaction. Now, in practice, you wouldn't use hydrogen cyanide because that's an extremely poisonous gas. So what you'd actually probably use is something like potassium cyanide, aqueous potassium cyanide, with a small amount of acid. And if you had aqueous potassium cyanide in acidic solution, you would form some hydrogen cyanide in that solution. You'd also form some free cyanide ions as well. So you wouldn't use hydrogen cyanide gas, you'd use potassium cyanide in an acidified solution, and this reaction would actually occur. And the overall reaction we've got there, and that is a classic example of nucleophilic addition to aldehydes, or it would work with ketones as well. What other reactions of aldehydes and ketones are possible? Well, hydrogenation is also possible, similar to what we saw in the alkenes. Hydrogen will react here with the carbonyl group in the presence of a metal catalyst, nickel or platinum really. So a nickel catalyst would facilitate this reaction. And again, what we would do is be an addition reaction. We would add the hydrogen across here, and we would form an alcohol. So we would add the hydrogen, basically an addition reaction, add the hydrogen in, hydrogen on there, hydrogen on here, and we form an alcohol. In the case of propanal, we would form propanol. If it was the ketone, so this was ethanol, we formed ethanol. If we had a ketone, so let's say we had propanone, again, we could add hydrogen across if we used a nickel catalyst, and what we would get in this instance is an alcohol, but this time we would get what we would call a secondary alcohol, because the OH is attached now to a carbon in the middle of the chain and not at the end of the chain as it would have been if we'd have used the aldehyde. So here we formed a primary alcohol, here we formed a secondary alcohol. Ethanol has formed ethanol, propanone has formed propan-2-ol. The final reaction of aldehydes and ketones that we're going to look at is reduction. And to reduce an aldehyde or ketone, you need to use a reducing agent. And there's two that you could use: lithium aluminium hydride, LiAlH4, or you could use sodium borohydride, which would be NaBH4. And in either case, basically these reducing agents are providing the hydrogen that are going to reduce this and turn it into an alcohol. So again, in the case of an aldehyde, what you will form is a primary alcohol. So in the case of ethanol, again, we're going to get ethanol. Or if you were to use a ketone, when you reduce that, you're going to reduce it into a secondary alcohol. So just like before, when we added hydrogen using a metal catalyst, this time we're using a reducing agent. Provide the hydrogen, and we're going to get, again, an alcohol. This time with the ketone, we're going to get, though, a secondary alcohol. In the case of propanone, we're going to form propan-2-ol. And there we are.